Okay, good morning, children. So now we are moving to our next chapter, that is wave optics. So in the last class, that is we discussed about ray optics, isn't it? Optics, it is the branch of physics where we discussed about the properties of light, isn't it? That branch is known as optics. And I told you that optics, it is classified as many, and we studied about ray optics there. That is the ray nature of light. That is when some phenomenon like reflection, refraction, dispersion, scattering, all these things we can explain on the basis of the ray characteristics. That is, light is traveling in a straight line. It's a straight path the light is traveling, and this is known as a ray. And we could explain all the phenomena which we are observing. That is like a phenomenon like a reflection, refraction, dispersion, scattering. All these things we could explain on the basis of the ray characteristics. That is light traveling as a straight path. Okay. Now we are moving to the next topic, that is wave optics. This is the wave optics. Okay. So that's a theory, that is the nature of the light, theory of the light. It is from the beginning stage, we can say that it is classified as many. So the first theory, it is given by Newton, and that is the corpuscular theory, and our ray nature is coming under this corpuscular theory of light. Okay, like the straight path the light is traveling. The next, Christian Huygens put forward that light is traveling not only as a straight path, it is traveling as in the form of a wave. That is, as the sound wave propagates, the light is also propagating as a wave. And he said that light is a longitudinal wave as sound wave, but later on it was proved that it is wrong. Light, it is transverse in nature. Then from that wave theory, after discussing about the electric and magnetic nature, that is the Maxwell proved that light, it is having the electromagnetic characteristics. It is propagating as a electromagnetic wave, that we know it is a part of the electromagnetic spectrum. And after that, Max Planck proved that not only this wave characteristics, it is having the particle characteristics, or it is having the quantum characteristics. So the last one, it is the quantum theory of light. Okay, so that is the studies about light. It is classified as the development is like this. First, it was believed that only that the ray nature, that is by Newton. Then wave theory comes, then electromagnetic nature, and this based on the electromagnetic nature only, it is proved that the light is not only not in the longitudinal wave, it is propagating as a transverse wave. Okay, sound wave is a longitudinal wave, but light is a transverse wave. Then it is having the ray characteristics, it is having the wave characteristics, plus it is having the particle characteristics, that is the light is propagating as a packet of energy, that is called quantum, that is by Max Planck. Okay, so in this, now we are going to discuss about the wave theory, that is the wave characteristics of light under the topic called wave optics. Okay, so what are the characteristics, how this wave nature is coming, and why it is proved that is it is having the wave nature. That is, based on this ray characteristics, we could explain only this characteristics. What is it? Reflection, refraction, dispersion, and scattering. Not only this, there are many characteristics shown by this light, that is we could observe in our day-to-day life, that is the interference and diffraction. Interference, diffraction, and polarization also. So what is this interference? Interference, you would see that if you are making a soap film, and when light falls, it gets reflected or not reflected, there are many a scattered colored pattern you could observe. Okay, that is like a rainbow color, but it is not orderly arranged. that all the 7 colors it is scattered on the oil film or the soap film. Okay, so that pattern it is known as the interference pattern. It is called the interference pattern. Then if you are hanging a CD and it's rotate like this, isn't it? That is, it oscillate. At that time we could see that again a colored pattern on that is CD. That is, all the 7 colors get scattered, and that pattern it is because of another phenomenon that is known as diffraction. It is called a diffraction, interference, diffraction. And one more thing is that is polarization. That is in Polaroids, that is in sunglasses, and all this phenomenon is using, that is polarization. So for trying to explaining how this phenomenon is happening, this we know, reflection, when light rays falls on a reflecting surface, it gets reflected back, isn't it? Smooth surface, it gets reflected back. Refraction, if it is going from one medium to another medium, there is a change in the path. And dispersion, we know that a single white light is falls on a prism. According to the wavelength, it is divided into different spectrum, scattering also. So this all could explain on the basis of the ray nature. But this, how is this happening? They fail to explain on the basis of ray nature. So what is that? That's another theory is developed, that is the wave theory. And on the basis of this wave theory, they could explain how this interference pattern is forming. That is a colored pattern on the surface of the soap film or the oil film. How is it forming? And diffraction and polarization. So that is not because of the, if light is traveling as a ray, all these things could not happen. But if you are considering light as a wave, it is propagating as a wave, traveling as a wave. And because of the superposition of wave, all these things are happening. All these things are happening. Okay, so on the basis of the wave theory, they could prove how this interference, diffraction and polarization is occurring. Okay, and who put forward this? It is by Christian Huygens. Okay, wave theory by Christian Huygens. So in this chapter, we will study what is this wave, how this wave is light is propagating as a wave. Okay, what is a wave front, and what is this Huygens principle in this wave theory of light. Then we have to explain what is this interference, what is this diffraction. Okay, so how this interference pattern like this diffraction, refraction and all, how this interference is happening and how this diffraction is happening. Okay, what are the theory and mathematical expression. Okay, then after that we will go for the not this chapter. Next chapter we have to study this electromagnetic nature of light and quantum theory of light also. So now let us discuss the first topic of this chapter, that is about wave front. What is a wave front? Okay, then we have to discuss about the Huygens principle in this wave theory of light. So what is a wave front? Okay, wave front. So what is a wave front? So you take the example, that is a silent pond and we are dropping a stone. Okay, just put a stone. So you can see that from the point where the stone is dropped, from that point onwards, there is a wave is propagating, isn't it? Wave is starting. So here, if this is the point, we drop the stone from like concentric circles, thus energy is spreading in all direction. Okay, the energy which we applied here, it is getting spreaded in all the direction the same way. Isn't it? I think you have observed that. So the same case here. There is a source. There is a source of light. From that source of light, the disturbance is originated and that disturbance is spreading in all direction, that is surrounding of that source with a same state of vibration, that is known as a wave front. You can see that crest and trough in that wave. isn't it? So crest means all the points are in the upward motion, isn't it? Trough means what? All the points are vibrating in the downward motion, isn't it? A wave, you know. Yeah. So this is the crest and this is the trough of a wave, isn't it? So here all the particles are vibrating in the upward direction, and here all the waves particles are vibrating in the downward direction. So that is a classification, crest and trough. So here from the point where the stone has dropped, from that is the source of energy. So that energy is distributed to all the particles in the water, isn't it? So here the particles in the water, in a point or in a location, all the particles are vibrating in the same direction. And the next to that, it is vibrating in the opposite direction. Then upward, downward, like that. Okay. So if you are joining all the points which are vibrating in the same direction, that is in the same phase. So here from this point, here is the wave. Here this is the next disturbance. Here this is the next disturbance. Here this is the next disturbance. Like that, all the disturbances are getting spread around the source, isn't it? And here I am joining where all the points are moving, all the particles are moving in the upward direction. So I will get a circle like this. Select. So the next point, if I am joining, there all the points are vibrating, all the particles are vibrating in some other, it won't be the maximum, it will be in the minimum. And the other, what is it? It is vibrating in the downward direction. Isn't it? And particles are vibrating in the downward direction. So I am joining all the particles which are at the same state of vibration. So we will get a, what is it? Region, and that region we will call it as the wavefront. So we can define it as the continuous locus. What is that locus? It is the connection of the points. Continuous locus of all such particles of the medium which are vibrating the same. Okay, vibrating the same at any instant. Okay, if all the particles are vibrating at the same phase at any instant, we can join that, and that is known as the, what is it, wavefront. For example, that you people are standing in a circle, isn't it? Standing in a circle, and you all hold your hands, keep one hand up and one hand down. So I am joining all the points where the upper hands you kept like this. I am joining all the points. This tip of the finger I will join, so I will get a circle. So that is a locus. So where all the points are in the upward direction. And now I can join all the points in your hand that is in the downward direction. You put down. Okay. So if I am joining all that point, I will get a circle down, isn't it? And one hand is here and another hand is here. So all of you are keeping like this. If I am joining all these hands which is stretched like this, the upward direction, I will get a circle. Okay, that is one locus. And one hand is kept like this, like here. Okay, not this much stretched, only here. And all the hands I am joining which kept in this position. So what is it? It is in the, this is the state, isn't it? Same state here. So joining that, I will get a locus of point, that is called another wavefront. So like that, particles are, one will be here, next will be here, next will be here. So which are the particles at this position? Which are the particles at this position? I am joining this, I will get a circle or a locus, not only a circle, any other shape maybe. So locus of continuous locus of all such particles of the medium which are vibrating in the same phase. Okay, same phase at any instant. That is known as same phase. At any instant, it is known as a wavefront. Okay, so wavefront we can represent here. If the source is a point source, the wavefront will be a circle. Okay, that is here. If you are standing in a circle and say that center part, it is the source. So what is it? We will get a circle. Okay, so accordingly, this wavefront we can classify it as wave. So then What is this? Ray also. So after that I will tell you, then I can rub it. Ray. So what is that ray? In a ray, that is, here we know the direction, isn't it? We studied that ray. It is originating from here. This is the direction. So an arrow drawn perpendicular to a wavefront in the direction of its propagation of a wave, that is known as the ray. So a wavefront, it consists of what? Ray also, which represents the direction of the wavefront. Okay, so we have to draw ray also there, that gives the direction of the wavefront. Okay, then this wavefront, it is classified according to the source. It is classified as spherical wavefront, cylindrical wavefront, and plane wavefront. That is according to the origin. According to the origin source, it is classified as cylindrical, spherical, and plane wavefront according to the origin or the source. Okay. So spherical wavefront we will get if the source is a point source. Okay, that's the example which we discussed. So here, what is it from this? This is the origin. Okay, source of the wavefront. So here the disturbance will come and particles are vibrating. So we are joining, all the particles are vibrating in the same phase. Okay, so I will get a wavefront like this. And this will be the next wavefront. This will be the next wavefront. So like that it will continue. Okay, same gap. And what is the direction of propagation here? The wave from the origin, it propagates outward, isn't it? So this normal is a perpendicular drawn, that is the ray, isn't it? That gives the direction of the wavefront. It will go like this. It will spread out in all directions equally. Okay. Then cylindrical wavefront. Spherical wavefront means the origin is a, or the source is a point source. Okay. And cylindrical wavefront, if the source is a linear source, that is, this is the source here. How will be the wavefront? Yes, all the particles will vibrate. Isn't it? All the particles will vibrate, isn't it? Here, this particle. So what is it? If we are joining that points, how will you get? You will get a wavefront like this in the form of a cylinder, isn't it? Here only that two dimension, only this waves are we are considering. So that is the spherical wavefront. Okay, and here around this is the source. So all the particles vibrate and we will join on this. So we will get a cylindrical wavefront. So this will be the wavefront. So this will be the next wavefront. So we are joining all the points which are vibrating the same phase. Okay. So here what is the direction of propagation from here? It is propagating. It is going in this direction, this direction, this direction, this direction. So this is the ray, isn't it? Which gives the direction of propagation. Same way the bottom also. Then the last one is plane. Plane wavefront we will get if the source is at infinity. Source is at infinity. Okay. If the source is at infinity, we know that the rays we are considering as a parallel rays, isn't it? If the source is at infinity, the light comes as a parallel rays. We studied that. So in that parallel, so here we are considering a position where all the particles are the same state of vibration. So this is a plane. The next one will be all the planes are at the same state of vibration. Next plane. Okay. So here the wavefront is a plane wavefront and it is in the separation also equal everywhere. Okay. So it is propagating like that. Wave propagates. Okay. So what is that? Wavefront. So from a point, from a source, what is it? That a disturbance comes or that point act as a source of this disturbance and it will spread out in all direction. And we will join all the points which are vibrating the same phase and that will give you a wavefront. And according to the source, we are having spherical wavefront, cylindrical wavefront and a plane wavefront. Okay, so this is the first one, basic thing about the wave optics. What is a wavefront? Okay, so what is a wavefront? It is the locus of all the points which is at the same state of vibration and ray gives the direction of propagation of the wavefront. And according to the source, there are three types of wavefront: spherical, cylindrical and a plane wavefront. So write down the question. What is a wavefront? What is a wavefront? What are the different types of wavefront? What are the different types of wavefront? Draw the diagram to represent each. Draw a diagram to represent each. Next question. What is a ray? What is a ray? Okay, so wavefront and a ray. Next is Huygens principle. So Christian Huygens. So wavefront we know. So that is Huygens principle will tell us about the propagation of the wavefront. From the origin, from the source, the one wavefront is originated and how the light is propagating as a wave. So that is explained by Huygens principle. So what is that? According to Huygens principle, each point on the wavefront is a source of next wavefront. So here, see, we are considering the spherical wavefront. This is the source, okay. And this is the, I am just drawing this side only. So this is a wavefront which we are getting. We are joining all the points which is at the same state of vibration. We got a wavefront. And this is the direction of propagation, perpendicular to any point, okay. So according to Huygens principle, each point, here you know there are n number of points, isn't it? N number of points are there. According to Huygens principle, each point on this wavefront is a source of next wavefront, and that is known as the secondary wavefront, or it is the wavelets. We call it as the wavelets, secondary wavefront or wavelets. So see here, I am considering this point. Okay, this point. So from this point, what is it? The next year, the disturbance will come. Isn't it? It can disturb or it can give energy to this point. So that disturb that medium. So it will provide disturbance and we can join this. Next wavefront is produced. That is the secondary wavefront. Or here consider this point here, that will be a source of next wavefront. That is the wavelets. It is known as the wavelets. Then how is the next wavefront originates? So while the propagation, the next wavefront is there. So that next wavefront is produced by joining the tangent of the secondary wavelets which are at the same state of vibration. So in between many will be there. So what is it? Joining the tangent. Here we will draw the tangent, and here this from here there is this point will be there. Here this point will be there, and from the source next wavelet will be there. This source next wavelet will be there. So I am drawing a tangent to this point and joining that. What is it? So that will form a new wavefront. So this is the next wavefront. It is getting by joining the tangent of the secondary wavefront or wavelets. Understood? And again from here also what is said here, this wavefront also there are many points. It will act as a source. So consider this one here, this produced. Okay, not too many other. So that we will join that, we will get the next wavefront. Then same thing it will repeat, it will propagate. Understood? And what is the speed of this secondary wavefront or the next wavefront? It is equal to what? The speed of the wavefront originated from the origin, or it is equal to the speed of the light in the medium. That is, the wavefront propagate with the same velocity of light in the medium. Understood? And here only this forward envelope. So here it is this side also we can consider, isn't it? We can join this and tangent will be there, and we can join this also, we will get a next wavefront. But that we won't consider, because here the direction, energy flows in the forward direction. There is no backward flow of energy. Okay, so from the origin, energy moves in the forward direction. So we will consider the forward envelope only, and that will be the next wavefront at the later time. Understood? So that is called that is the Huygens principle. So secondary wavelets are originated and it will propagate with the same velocity. Okay, so this is a very important principle on this wave optics. All the discussion are coming on the basis of this Huygens principle. Okay, so what is Huygens principle? These are the statements of Huygens principle. So write down the next question, state Huygens principle. So what is it? Each point on a wavefront act as a source of secondary waves or wavelets. The secondary wavelets spread out in all directions with the speed of light in the given media. And the new wavefront at any later time is given by the forward envelope. So I think you understood that forward envelope. So from here, the source and these are the secondary wavelets. So we will join this forward envelope. Okay, that is the tangent drawn to all the points. Okay, the same state of the secondary wavelets at that time. Okay, so in this time, this is the next wavefront. Then here, this is the source. So you will get secondary wavelets, and joining the tangent, we will get the next wavefront. Okay, so as such, it continues. So that is the propagation of the wavefront. So Huygens principle is a very important one. So if it is a point source, it will be what? If the source is a point source, it will be circular. So it's spherical wavefront. And if the source is a linear source, so what is it? Here, all the points will act as the source of secondary wavelets. So from this point, there is a wavelets produced like this. Wavelets are produced from each source. Many will be there, okay. And joining all the points at the same state of vibration, that is the forward envelope. So this will be the next wavefront. And here, okay, and here what is it? In this wavefront, all the endpoints will act as the source of secondary wavelets, and here the wavelets are produced. Like these wavelets will be produced, and joining the tangent at the same state, you will get the next wavefront. Like that, it will propagate. And here, this is the first wavefront, and these are the secondary wavefront or wavelets. Joining this, you will get the wavefront. Then all the points will be there. Wavelets will be produced, and joining the tangent, we will get the next wavefront. Okay, so this is from a point source and this is from a plane source or the linear source. Okay, so that is the propagation and Huygens principle. So write this and study this carefully. Okay, this is a 2-mark question. State and explain Huygens principle. Very important. Write down next question. Explain the Huygens geometrical construction. Explain the Huygens geometrical construction for the propagation of A. Spherical wavefront, B. Plane wavefront. Spherical wavefront and a plane wavefront. Okay, so then you can copy from your textbook. That diagram is there in your textbook. Next, we have to discuss the application, that is Huygens principle, and using Huygens principle, we have to prove the laws of reflection and refraction. Laws of reflection and refraction. Using the ray nature, we already proved that. And if the light is coming as a wavefront, okay, let's say it is propagating as a wave, there also we have to show that it is obeying this laws of reflection and laws of refraction. That is, derive the laws of reflection of light on the basis of Huygens wave theory of light. So that is the next question. Okay, laws of reflection. We know what is laws of reflection. What is laws of reflection? Angle I is equal to angle R. So then, angle of incidence is equal to angle of reflection, and incident ray, reflected ray, and normal lies in the same plane. Okay, or should be in the same plane. These are the statements. So we have to prove that is in the case of the wave nature of light also. So here this is our reflecting surface. Okay, diagram you have to draw carefully. So look at the diagram how I am drawing. Diagram here it is very important. Okay, so this is the reflecting surface. Okay, and we are considering that the loss of reflection we are consider ray optics. What is that? The source is at infinity. So a ray is coming. So here instead of a ray, what we have to consider? We have to consider a plane wavefront is coming. This is a wavefront. Okay, that is from the origin. We have seen how the wavefront is propagating. Okay, so this is the wavefront and we can represent the direction with a ray. So it is coming from infinity. So the parallel line gives the direction. Okay, so this is the wavefront and I am naming it as A, B. Okay, it is AB. And here we can draw the normal to this point. This normal. So here we can say this is the angle of incidence I. Isn't it? That is the angle of incidence. Okay. So this is I. This angle is also I. Is it? This angle is 90 because this is the normal. This is 90. Therefore, this angle is 90 minus I. This angle is 90. So, this will be 90 minus 90 minus I. Therefore, that angle is I. Okay, like that we are getting that angle is equal to I. Normal I. And this is AB. Okay. Okay, so this is the diagram. What is happening here? According to Huygens principle, each point on this wavefront will be a source of secondary wavefront, secondary wavelets, isn't it? So now you can see that this point A reaches on the reflecting surface. Point A reaches on the reflecting surface. By the time other points on this wavefront does not reach on the reflecting surface. So this point A reaches on the reflecting surface and it started reflection. So from here, what is that secondary wavelet? That secondary wavelet will be a reflected wavelet, isn't it? It gets reflected from here. So that reflected wavefront originated and it is propagated. Okay. So after some time, only this B, the point B, reaches on the reflecting surface, isn't it? It will take time. We can take the time T. After time T only, this point, that is this B, reaches on the reflecting surface and we can take that point as C. So by the time what is happening here from A, the reflected wavefront are produced and if we are joining the envelope, we can say that it reached here. That is the reflected wavefront, that is from here, that point reaches here. So one by one, all the points reached on the reflecting surface and it produced the reflected wavefront. And after time T, if you are joining all such locus, we will get a plane wavefront like this and we can name it as DC. And this DC will be the reflected wavefront. Okay, DC will be the reflected wavefront. And what is the time taken by this D from A to reach at D? It will be the same time, that is T itself. Okay, that is within the time T only B reaches on the reflecting surface C, by the time from A, the reflected wavefront will reach at D. So 1 by 1, that is next time t minus next 1 second, 2 second, like that, this will reach here. Okay. So at T, B will reach at C. So joining all the points, we will get a reflected wavefront. And what will be the direction? The perpendicular drawn, that is the ray, will give you the direction. So this is the incident wavefront and this is the reflected wavefront. Okay, so that is the time difference only. Okay, so this is the time taken. So within the time T, only A reaches D, by the time only B reaches at C. Okay, so at that time when B touches C, we got a reflected wavefront. That is, the secondary wavelets originated from all other points other than B. Okay, then draw the normal here, and this angle will be the angle of reflection R. Isn't it? Reflected ray and normal will give you the angle of reflection R. Okay. Then here in this medium, this is a medium, and here the velocity of light is, we can take it as velocity of light is V. Light is equal to V. So what is the distance BC? What will be the distance BC? Therefore, BC is equal to V. Thus, wave is propagating with the velocity V, and the time taken by the wavefront to reach from B to C is T. Therefore, the distance BC is equal to velocity into time T. Okay. And what is AD? AD also same, isn't it? That is, from A, the secondary wavelet reaches at D. That is, the reflected secondary wavelet reaches at D within the time T. And what is the velocity? That velocity is equal to Vt again. Okay. Then you can see two right angle triangles in this. Two triangles in this figure. So which are they? That is triangle ABC. ABC. That is the triangle made by the incident wavefront. And what is the next triangle? ADC. That is by reflected wavefront. ABC and ADC. Okay. In ABC and ADC. So in ABC and ADC, you can see that this angle B and D are same. Isn't? And here this AC is a common side for the both triangle ABC and ADC. Then what can we do? So what can we write here? Here, from comparing these two triangle ABC and ADC, what is it? We can write AC is equal to AC, isn't it? Then angle ABC equal to this angle. Angle ABC is equal to angle ADC. Then what else? Yes. This side BC, isn't it? We got BC and AD are equal. BC is equal to AD. Therefore, what is it? Yes, this angle, isn't it? This angle is I. And what is this angle? This angle is R. So this angle is 90 minus R. Therefore, this angle is equal to R. Isn't it? This angle is I and this angle is R. Therefore, we can write angle BAC is equal to angle DBC isn't it? BAC. This angle will be equal to DCA. What is BAC? That is angle I is equal to angle R. Okay. So that is the laws of reflection. And it is very clear that all the incident wavefront, reflected wavefront and all the normals drawn are in the same plane. Okay, so hence laws of reflection of light on the basis of Huygens principle is proved. Okay, so here draw the diagram, label everything and write this. Okay, so this is the condition. And what is the last step? Here we have to write and incident wavefront reflected wavefront and normal lies in the same plane. Hence, laws of reflection of light is proved. Okay, so here the important one is the diagram with the labeling. So draw like this. Okay, I think it's clear, and all these steps. Then is the last steps. So laws of reflection consist of two steps: angle of incidence and angle of reflection, and this one. Okay, so that is the laws of reflection. Next, we have to prove laws of refraction. Okay, laws of refraction on the basis of Huygens wave theory. So, what is laws of refraction? Yes, incident ray, refracted ray and normal lies in the same plane, and sin I by sin R, sin of angle of incidence divided by sin of angle of refraction is a constant, that is called the refractive index. Okay, is the refractive index. So the same thing. Okay, so here and the refraction, two cases are there. One is the ray of light goes from denser to rarer medium, and the other one is rarer to denser medium. Okay, so in the case of ray optics, when we are considering the light as a ray, what are the things we discuss? The same thing is coming here also. So here instead of ray, we are considering the wavefront. So first we will discuss about the rarer to denser medium. So this is the separation. Okay, so here we can take this is rarer of refractive index N1 and this is denser of refractive index N2. Okay, so here the wavefront is coming, then that is a plane wavefront. It is coming from infinity. Okay, so it is a plane wavefront. So this is the wavefront. Okay, you have to represent it like this, wavefront. So this is the incident wavefront. We can name it as AB. And here we can draw the normal. So what is this angle? Is I, and this is also I. Okay, same thing. Both angles are I. And here, what is it? Yes, this point reached on the refracting medium or refracting point. So what happened? The source of secondary wavefront, and from the source the wavefront, secondary wavefronts form, and that will be the refracted wavefront. Okay, refracted wavefront. So this point reach here, this refraction occur. Next point reach on the refracting surface, refracted wavefront produce. Next point, so like that all the wave point reaches on the refracting surface or the interface, and after some time only this B reaches here. It takes time t to reach from B to D, that is B, the point B, to reach at D. That is the source of the wavefront, isn't it? Secondary wavefront that reaches at D after time t. So by the time what is happening is from all this point, like the refracted wavefront originated and joining all the tangent, what is it? You will get a wavefront, and that will be the refracted wavefront. This joining this tangent, next to tangent, next to tangent, next to tangent, like that joining, you will get the refracted wavefront. Okay. Refracted, you got a refracted wavefront like this. So what's the time? T time, right? From the time T, within the time T, B reaches at D. By the time from all the points the refracted wavefront originated. So we can join it like this. That is, if ray of light goes from rarer to denser, it bends towards the normal. So this is the refracted wavefront. And what is the direction? The direction will be given by the perpendicular drawn to this. Okay, so this is the refracted wavefront. Okay, then draw a normal to this point. What is this angle? This is the angle of refraction R. So this is the direction of the refracted wavefront. So this is the angle of refraction, and here also this is R. Okay, so this is R. This angle will be R. This is also R, angle of refraction. Okay, so here what is the time? So here we can take this point as C. So from B, the point reaches D. By the time from A, the refracted wavefront reaches at the C and is taken same time T. Okay, by the time T only, that is T is the time taken by the source to reach from B to D. By the same time from A, the refracted wavefront reaches at C. Okay, so one by one from all the points the refracted wavefront are coming. And we are joining all the points at the same state of vibration. We got a refracted wavefront. Okay, then again the same procedure. Considering the triangle, we are having the triangles here. Which are the triangles? We have triangle A, B, D and triangle A, C, D. Now, A, C, two triangles. And what is AC? What is AC? AC and BD we have to find out. AC and BD we have to find out. And here the difference is, here the velocity of the light is V1 and here the velocity of light will be V2. Okay, V1 and V2. Because here the medium is different. So in two medium, the velocity of light will be different. In refraction, it is in the same medium. So we have taken the velocity as V. Here, the first medium, we can take the velocity of light as V1. And the second medium, the velocity is V2. So what will be AC? Here the velocity is V1. So AC is equal to, sorry, here the velocity is V2. So AC is equal to V2 into T, and here we can write BD. Okay, it's a triangle BD. So BD is equal to V1T and AC is equal to V2T. Okay. In this diagram, we have to get this relation sin I by sin R. Isn't it? We know that already. So from this triangle, we can find out what is sin I and what is sin R. So what is sin I? From the first triangle, we will get sin I. What is sin I? Sin I is opposite side. What is opposite side? BD by adjacent side is AD. BD by AD. And sin R is equal to, from this triangle, we will get sin R. Sin R is equal to AC. AC by opposite side. By adjacent side is AD. AC by AD. AC is V2T and here it is V1. So find out sin I by sin R. Therefore, sin I by sin R is equal to BD by AD into AD by AC. AD get cancelled. Sin I by sin R is equal to, what is VD? We got it, that is V1T, and AC is V2T. TT get cancelled, so it is equal to V1 by V2. We got this as the ratio between the velocities, that is V1 by V2. So how will you relate it with the refractive index? This is how the velocity and refractive index related. So what is the definition for refractive index? Yes, it is the ratio between the velocity of light in air divided by velocity of light in medium. It's a refractive index of medium. So we can write it as N21. N21, refractive index of second medium with respect to first medium. V1 by V2 is equal to N2 by N1. Okay. So it is N21. So it is proved sin I by sin R is equal to refractive index of the medium. And what is the next statement? All this incident wavefront, refracted wavefront, and all the normal lies in the same plane. Hence, this loss of refraction is proved. Okay, so this is the case when the ray of light goes from rarer to denser. And if it is going from denser to rarer, what is happening? Denser to rarer, the refracted ray went away from the normal. So denser to rarer. So only the difference in the diagram. Instead of coming towards this, it will be going like this. This diagram will come like this. Incident wavefront. This will be the refracted wavefront. It will come like this. This is I and this is I. This is R, this is R. Only this this shifting from here to this side. All other things are same. So that you do as your work assignment. So next one B is denser to rarer. Draw the diagram and all the steps are same as such. Okay, everything will come as same. So here the velocity is V1, here the velocity will be V2. Okay, so that is your homework question. That is, derive the law of reflection of light on the basis of Huygens wave theory when a ray of light goes from denser to rarer medium. Okay, so that is about the wavefront Huygens principle and its application in the laws of reflection and refraction. Applying Huygens principle to prove the laws of reflection and refraction. Okay, so that is all for today. Complete your notes. Okay.